Alright, so at the end of last week we started talking about coordinate vectors. We kind of went down talking about coordinate vectors because what we wanted to do is we wanted to take these linear transformations that we have and turn them into a matrix form. So the reason we wanted to do this is we can't just say take something in P2 and multiply it by a matrix and have it make sense the way we want to. So we took 1, 2, 3, 4 times the polynomial ax squared plus bx plus c. We're not really sure what this is going to do. This is going to be some sort of weird nonsense stuff that won't necessarily give us the thing that we want. So our key is going to be to use coordinate vectors that we talked about at the end of last week. So if we have a basis for our domain for a transformation, let's say it's v1 through vn, this set B, then what we want to do is we want to find the coordinate vector. What we can do with for our coordinate vectors is we can represent some vector based on its linear combination of these basis vectors, and how we get to that. And what we're going to do is we're going to talk about taking some transformed vectors, writing them with a different coordinate basis, and then using that to help us create our matrix. So our goal is going to be to make it so that if we take our matrix times some vector written in terms of the basis for the domain, our output should be whatever the transformed version is of that vector written with respect to the basis of the codomain. Alright, so let's talk about kind of going through the process for doing that. So let's talk about our steps for finding the matrix form of linear transformation. In the end, the big thing we're going to need to worry about is mapping our basis elements. So if we wanted to go and take a transformation going from v to w, for the example we're going to kind of walk through to kind of show and highlight some of these steps. Say we wanted to go ahead and go from p2 to m2 by 2. The first thing what we want to do then is we want to transform 1. If we transform 1 using this, what we should get as output is the matrix 0, 0, 1, 0. We want to transform x. So here what we'll get as output if we put in x should be 0, 1, 0, 1. And if we transform our last basis element, which is x squared, we should get as output 1, 0, 0, 1. The next thing we're going to do is we're going to take each of these outputs and write them as coordinate vectors with respect to the basis for our codomain. In this case, this basis. So here if we wanted t1 and we wanted to write that with respect to the basis for the codomain, what we're doing is we're figuring out what linear combination of these would end up giving us this vector, and then writing that as a vector in this case R4, because there are 4 of these. So here we would have 0, 0, 1, 0. And you can kind of review from our conversation last week about coordinate vectors how we're finding this, and if you're still not sure after reviewing, definitely ask in the comments. Definitely want to know what your guys' questions are. We also want to take our t of x and write it with respect to the coordinates, the base for w, or in this case, the basis for m2 by 2. And so we want to figure out how we can get 0, 1, 0, 1 by adding these up. And that will be 0, 1, 0, 1 in this case. And then we want to figure out how we write this transformed version of x squared in terms of the basis for w. And in this case, it'll be 1, 0, 0, 1. So we get each of these different transformed coordinate vectors. So we take these basis elements, we transform them, and then we form coordinate vectors with them. And what we'll do is we'll create our matrix by taking each of these vectors in the order we found them as the columns for our matrix. And so our matrix is going to be found by making the first column, column 1, will be whatever t of 1 written with respect to the basis for w was. Column 2 will be whatever t of x was written with respect to the basis for w. And column 3 will be whatever t of x squared was written with respect to the basis for w. So in our case, it will be 0, 0, 1, 0, 0, 1, 0, 1, and 1, 0, 0, 1. So we'll just take each of these and make them a different column of our matrix. So the last thing you can do, it's kind of a useful but optional step, is you can check to make sure that the matrix will do the same thing as our original transformation. So let's do this. Say I had ax squared plus bx plus c. I wanted to transform it. That gives us a, b, c, a plus b. And so what we want to do is we want to take ax squared plus bx plus c, and we want to write it in terms of our basis for v. So we want to do this coordinate vector thing we had talked about. And so if we're using this basis here, we want to go ahead and take whatever the constant term portion is and write it first, then the x portion, then the x squared portion. And so remember, we're really just saving the coefficients at this point for our linear combination. So we should get c, b, and a as this coordinate vector. Then what we'll do is we'll take our matrix that we found and multiply it by this c, b, a. So we will take 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, and multiply it by c, b, a. And so when we do this multiplication, the first entry is going to be 0 plus 0 plus a. So a. Next entry will be 0 plus b plus 0, so b. And then we'll have c plus 0 plus 0, so c. And then we'll have 0 plus b plus a, or just a plus b. Now when we write this a, b, c, a plus b, this is still a coordinate vector written in terms of these elements here. So what this really equates to is saying that we have a times 1, 0, 0, 0 plus b times 0, 1, 0, 0 plus c times 0, 0, 1, 0 plus d, or not d, sorry, times a, or plus a plus b times 0, 0, 0, 1. I'm running out of page. And if you do this, you'll find that this gives us the exact same thing as we had before with the a, b, c, a plus b. So this does do the thing that we want it to do. Notice that the dimensions of our matrix are going to be based on the vector spaces we're going to and from. So for example, P2, what we started with was a three-dimensional vector space because it had a basis with 3 elements. And so because of that, we're going to have 3 columns because the number of columns has to equal the number of rows of this vector. And our output, since it needs to be something in 4 dimensions, because M2 by 2 is a 4-dimensional vector space, that's going to be the number of rows of our matrix. So here we have an n-dimensional vector space and going to an m-dimensional vector space after the mapping. The matrix is going to be m rows and n columns. Just kind of something cool to think about. All right, so let's say we wanted to find the matrix form of this linear transformation going from P1 to P2, where ax plus b gets transformed into a times x squared plus a plus b times x minus b. So since we're going from a domain of P1, which is a 2-dimensional vector space, to a codomain of P2, which is a 3-dimensional vector space, the matrix we're going to create should have 3 rows and 2 columns. All right. So what I want you guys to do is, if you feel confident after that, seeing that example that you could create this matrix form, take a moment, pause, and then give it a go. And if you don't feel so confident, kind of watch until you get to a point where you feel confident. Note that if you choose different bases than I do, it doesn't mean you're wrong, it just means that you're going to need to take a moment to kind of check, make sure you're oriented the same way. So I'm going to go ahead and create a basis for the domain V, which is P1, and our codomain W, which is P2. So V is P1, W is P2. So for V, I'm going to use x and 1, and for W, I'm going to use x squared, x, and 1. Again, if you switch to the order of these, it's not that important. The big thing is that you're consistent when you use things going forward. So like on the previous page, that our basis for P2 is going to be 1xx squared. Here we're saying it's x squared, x, and 1. It doesn't matter which you use as long as you're consistent. It will change what your final matrix looks like, usually just in terms of what the rows and columns are, but it won't be something so detrimental that I won't be able to figure out whether or not you're doing things correctly. So don't worry too much about that. All right, so the next step, once we found our bases, is to take each element of our basis for our domain and find its image after we apply the transformation. So here is our transformation. So if we have t of x, that is going to become x squared plus x. So kind of the idea here is if we're doing the ax plus b and we're comparing it to the x, here we can see that a has to be 1 and b has to be 0. There's no constant part and there's just one of the x part. And so we can use that knowledge of a and b as our inputs to plug in here. So we get x squared plus x. And if we want to transform 1, that'll just be the b portion. So there'd be a 1 for b and a 0 for a. So our output should be x minus 1. Okay. So the next thing we need to do is take these images or outputs of our transformation for our different basis vectors from the domain and write them with respect to the codomain as coordinate vectors. So if I take t of x, write it with respect to the basis for the codomain, what I'm trying to do is take x squared plus x and write it as a coordinate vector in terms of this. So really, we want to think of this, remember, with coordinate vectors as being x squared plus x equals something times x squared plus something times x plus something times 1. Because we're using the standard basis, we can pretty easily tell it's a single x squared plus a single x plus no constant part, so 1, 1, 0. And then when we're looking at transforming 1 and then writing it with respect to our basis for our codomain, we're taking x minus 1 and writing it with respect to that basis, so it's something times x squared plus something times x plus something times 1, so it's 0x squared plus x minus 1. So we've got our coordinate vectors now, and last but not least, we can go ahead and just combine these two vectors as our first and second columns for our matrix. So we have 1, 1, 0 as the first column, and 0, 1, negative 1 as our second column. And just to check, this has, as we thought, 3 rows and 2 columns. Now we can check this with some arbitrary thing, or we could try a particular input. So here, let's look at a particular input. So if we look at t of 8x plus 4, t of 8x plus 4 is going to be, so remember that our transformation is supposed to be ax squared plus a plus bx minus b, and so the a comes from the number in front of the x, so in this case it's 8, and the b comes from the number that is just the constant portion, in this case it's 4. So here we will get 8x squared plus 8 plus 4x minus 4, which will be 8x squared plus 12x minus 4. Now we want to check to make sure that this does the same thing as taking our matrix of 1, 0, 1, 1, 0, negative 1, and multiplying it by 8x plus 4, but written as a coordinate vector with respect to our first basis. So if we want to take 8x plus 4, with respect to this, it is going to be, let me just rewrite the matrix first, we will have 8 times x plus 4 times 1. So it'll be 8, 4. And so when we do our multiplication, the first entry is going to be 8 plus 0, so 8. The next entry will be 8 plus 4, so 12. The last entry will be 8 plus negative 4, so it'll be negative 4. And so we need to take 8, 12, negative 4, and we're recognizing that this is a coordinate vector with respect to the basis for w. And so if we write it then in terms of this, what we're really seeing is 8x squared plus 12x minus 4. And so as you notice, as we got the same thing, whatever way we did it, and so that'll work for us. Okay, great. So let's go through maybe a little bit of a easier example. So let's say we wanted to go through, and easier is maybe a bit relative. It makes you think and scratch your head a little bit. Let's say we wanted to find a matrix representation of this linear transformation that went from R3 to R, and figure out what that matrix is going to look like. So what I recommend you do first is pause the video here and go through the steps. See how far you can get kind of without any extra help. I love these pauses. It gives me a second to take a drink of water. All right, so let's find that basis for R3, which we'll call B of V. And that, for us, is going to be the standard basis of 1, 0, 0, 0, 1, 0, 0, 0, 1. Now note, you did not have to use this basis, but it's the standard basis. It's the one that I'm hoping jumps to your mind every time you see R3. I hope you see, yes, this is a basis I would like. It would be the easy one. It would be the one that would be super useful to use. And then we also need a basis for our codomain, which is R. This will be our BW. And so here, it's just going to be single number, so it's going to be 1. And so now what we need to do is, since this was our first step, steps 2 and 3 will find us transforming these vectors using the transformation and then writing them in terms of this basis. So if we want to take and transform 1, 0, 0, and then write it with respect to this basis, we'll get, since we take A, B, C, and it's A plus B plus C, we're really just adding all these up, so 1 plus 0 is 1, but we need to figure out how to write that as a coordinate vector with respect to this basis. So if I want to figure out how to get 1 by taking 1 times some number, well, that number is going to be 1. So we'll get 1. we need to do that as well with 0, 1, 0 and 0, 0, 1. So 0 plus 1 plus 0 is 1. We write it as a coordinate vector with respect to this basis. We get 1. And then for the most shocking part of this, if we take 0, 0, 1 and we add all of those together, we get 1. You need to write it with respect to this coordinate, this base R, and we'll get 1. And so our matrix is going to be found by taking each of these values, each of these vectors that we found, and writing them as columns of our matrix. So our matrix should be 1, 1, 1. So if you took 1, 1, 1, and you multiplied it by the coordinate vector form of A, B, C, you should get A plus B plus C as an output in terms of this basis, and then you'd write it in that basis, and you just get A plus B plus C. So it's kind of nifty, very cool. Okay, maybe I think it's cooler than everybody else, but that's besides the point. The point is we can get matrix forms, which are nice because we can code them pretty well. Alright, so let's say we wanted to go ahead and look at the linear transformation going from R2 to R2, where t of xy becomes x plus 2y and x minus 2y. We want to figure out what matrix form we're going to have for this transformation, and we also want to know if we had a linear transformation be defined as t of xy times this matrix, or is equal to this matrix times xy. We want to know how it could be written in terms of this. So we want to both take the transformation and figure out what its matrix is, and we want to take a moment to see if we can take a matrix and figure out what it's doing transformation-wise. So take a moment, see if you can figure these out, and then come back. Alright, cool, you're back. So we want to make sure is that if we took whatever the matrix is times xy, we would get the proper output. In this case, it would be x plus 2y and x minus 2y. So then this first row will be, this first row of our output will be how we figure out what this is. So we should have 1x, so we should have a 1 there, and we should have a plus 2y, so we should have a 2 there. All right, we don't want to include the x and y in the matrix because they're already going to be part of this vector that we're multiplying by. Then our next row should help us take a single x and then minus 2y. So 1, negative 2. So it should be b. All right, and then last but not least, we want to go ahead and look at this linear transformation. And what we're doing is we're taking negative 1, 0, 0, 1 times xy. And so as output, let's see what we get. The first entry should be negative 1 times x, so negative x plus 0, just negative x. And the next entry should be 0 plus y, so y. So we should get negative xy as our output. Okay, so hopefully so far seems pretty clear. The one more example we're going to have for the moment is trying to look at subspaces. So we talked about subspaces before. Things get a little bit tricky if we try to use them for these matrix representations. So let's say we wanted to find a matrix representation of a linear transformation going from some complicated vector space like this to P1. So our first step, remember, is to find our bases. So here, the basis for P1, which we're going to call BW, is pretty easy to figure out. It's just x and 1. What we don't know yet is the basis for V. So V is going to be the set A, B, C, 0, B minus C, 2A. So that much we are given above, where A, B, and C are in the real numbers. Now, from some of our stuff before with subspaces, we should want to go ahead and try to write this as the span of some vectors. So if you don't remember how to do this, maybe take a moment and play around with it. Go back to earlier in the notes and see if you can figure out what I'm about to write. And if you think you've got a good guess, then keep watching the video. So this should be the span of 1, 0, 0, 0, 0, 2, 0, 1, 0, 0, 1, 0, and 0, 0, 1, 0, negative 1, 0. Okay, so this, having our spanning set is nice, but this doesn't give us a basis yet. So is a spanning set, woo, but not yet a basis. We need linear independence still. Alright, so let's go ahead and figure out if these three vectors are linearly independent. So what we'll do is we'll take some alpha times 1, 0, 0, 0, 0, 2 plus, maybe we'll make it alpha 1, plus alpha 2 times 0, 1, 0, 0, 1, 0 plus some alpha 3 times 0, 0, 1, 0, negative 1, 0. And we want to set it equal to the 0 vector. And we want to determine and make sure for linear independence that we have exactly one solution to this problem. So let's figure out what our system of equations is going to be. We'll start off using the top left entries, so we should get that alpha 1 equals 0. Top middle entries tell us that alpha 2 equals 0. Top right entries tell us that alpha 3 equals 0. Make this a little bigger. Our bottom left entries tell us that 0 equals 0, and while that's true, it's not very exciting. Our bottom middle entries tell us that alpha 2 minus alpha 3 equals 0. And our bottom right entries tell us that 2 alpha 1 equals 0. Well, without even going ahead and putting this into a matrix, we can tell just from these three entries that alpha 1 has to equal 0, alpha 2 has to equal 0, and alpha 3 has to equal 0. So we have exactly one solution. So we have linear independence. So then combining the fact that we have a spanning set with the fact that that set is linearly independent, our basis for V, which we'll call B sub V, going forward is going to equal this spanning set. So 1, 0, 0, 0, 0, 2, 0, 1, 0, 0, 1, 0, and 0, 0, 1, 0, negative 1, 0. Alright, so we've got our basis. That was just step 1. So now we need to go ahead and transform for steps 2 and 3. We need to take each of these vectors, transform them, and then write them in terms of our other basis for our codomain. So let's figure out what happens. So if we want to take h of 1, 0, 0, 0, 0, 2, so this is where we want to take a moment to pause. When we take a look at this transformation, it's saying that we take something of the form a, b, c, 0, b minus c, 2a, and we set that equal to ax plus b. What we would need then is to know what a is, what b is, and what c is, so that way we could go ahead and properly make this transformation. Fortunately, these are already conveniently written in terms of these basis vectors. So the inputs that were given for our transformation happen to be in this form already. So here, the A part is just going to be 1, because it'll be 1 for that, and then we got zeros for the B's and the C's. So we have 1A, 0B, 0C, so we should end up with 1 times x plus 0, so we should just end up with x. So we want to take this, and we're going to eventually write it in terms of our basis for our codomain. So we have x, and we're going to write it with respect to the basis for our codomain, and we end up getting 1, 0. Feels like a lot of work to just get 1, 0, but let's work. All right, we next want to take our next vector, 0, 1, 0, 0, 1, 0, and we'll write it in terms of our basis for our codomain. So what you'll notice here is this is going to be our B portion, right? So if we have our A, B, C, 0, B minus C to A and C are 0 and B is 1, but all we really use here are A and C, and so this part will be 0, it'll be 0x plus 0, so it'll just be 0. So we need to figure out how to take 0 and write it in terms of our basis for our codomain. In this case, it's going to just be 0, 0. And then last but not least, we got one more basis vector to transform, 0, 0, 1, 0, negative 1, 0. And so we will take this, write it with respect to our basis for W. And so again, we'd want to figure out how to take this and figure out how it plugs into this function. Here it means the A and the B portions are going to be 0, and the C portion is going to be 1. So it'll be 0x plus 1, or just 1. So then we need to determine how we can go ahead and write this 1 in terms of our basis for our codomain, and that's just going to be 0x plus 1. So then our matrix at the end of all of this is just going to be 1, 0, 0, 0, 0, 1. So if we were able to take some sort of input and break it down into our A, B, and C component, then what we could do is we could take that and multiply by this matrix. It would give us an output of AC, and then we could transform that using these to get whatever the AX plus C was going to be. Now there's a reading example on the next 2 pages in your notes. Then we move on to getting into a ICE that will let us start playing around with trying to find these matrix representations, and we'll kind of escalate it as things go. So take a minute to read that example in the next 2 pages that maybe will help piece things together, and then come into the next video where we look at ICE 5.